This section explains how a single first-order condition generates the whole field of asset pricing. One first-order condition generates the entire field. An investor trades a marginal bite of consumption today for the asset's payoff tomorrow. At the optimum, the marginal utility surrendered equals the marginal utility gained, which forces price to equal the expected payoff discounted by the marginal utility ratio. Everything else is a special case. Read off this. Interest rates track expected marginal utility growth, and a risk correction is a covariance of payoff with marginal utility, never a variance. The step that does the work is what you feel. What you feel is marginal utility, a transform of consumption rather than consumption itself. The rest of the book is the hunt for observable proxies against which to compute that covariance. The whole edifice is one equation seen from different angles. This section explains why every asset price reduces to a single equation. Every price collapses to one expectation. Price equals the expected value of M times X. Price equals the expected product of the payoff X and a single stochastic discount factor M, and the entire subject is just specializations of this. The step that makes everything follow is the factoring. You split the pricing problem into two pieces, the equation, which is always true, and M, where the model actually lives. Do that, and a stock, a bond, an option, an excess return all become one theory for all asset pricing, differing only in what you substitute for X. Every rival model, whether the CAPM or power utility consumption, is merely a different function tying the same M to data. All risk correction is then nothing but the covariance of M with the payoff. This section explains why one equation carries the entire chapter. Everything in the chapter falls out of a single recognition. The statement that price equals the expected value of M times X is a first-order condition, and a first-order condition is an equation. An equation constrains a joint relationship. It ties together price, payoff, and marginal utility all at once, without ordering which one is cause and which one. Its one is cause and which is effect. There is no causal arrow inside it. Because it only constrains a joint, it survives the removal of nearly every structural assumption. Complete markets can go. Assumptions about return distributions can go. The two-period horizon can go. Equilibrium itself can go. The equation still holds. It holds per investor, per asset, at the margin. It is the willingness to pay for a little more payoff, because a little more is all a derivative sees. So the chicken and egg question dissolves. Does consumption set prices, or do prices set consumption? Neither ordering is forced. Know either side, and the equation hands you the other. This section explains how little the central pricing equation depends on its surroundings. The whole chapter is one move. Price equals the expected value of M times X is a first-order condition, and a first-order condition does not care about the world it sits inside. Strip complete markets, normal returns, quadratic utility, two periods, no human capital, even equilibrium itself. None of them were doing the real work. Each only buys a convenient special case later. Because the condition is marginal, it also runs in either direction. Know the discount factor and you read off the price. Know the price and you read off consumption. That is why Cochrane's chicken and egg, the endowment economy versus linear technology, dissolves. The same first-order condition characterizes any equilibrium, whichever variable you happen to call exogenous. Chapter 1 hands you the equation. Here you learn how little it costs to assume. This section explains how any asset's price breaks down into the prices of elementary bets on single states. Start by decomposing any payoff into its atoms. A contingent claim pays $1 in exactly one state and 0 everywhere else. So any asset is just a bundle of these claims. Holding X of 1 is a claim on state 1, X of 2 is a claim on state 2. Frictionless markets cannot price the bundle apart from its parts. This is Cochran's Happy Meal theorem. The meal costs whatever the hamburger, the fries, the drink, and the toy cost separately. So price is forced to be linear. The price of the asset equals the sum over states of the state, price times the payoff in that state. Now the whole chapters move, multiply and divide by probabilities. Define M of S as the state price of S divided by the probability pi of S. The sum then becomes the expectation of M times X. The discount factor was never exotic. It is the state price per unit of probability. Existence, positivity, and linearity all fall out of prices and payoffs alone. There is no utility function anywhere. This part lays out the single structural move behind asset pricing. Every asset is a bundle of bets, each paying $1 in one state of the world. Its price is just the sum of those states' prices. Cochran calls this the Happy Meal theorem. The price of the meal equals the price of its parts. Divide each state price by its probability, and the sum turns into an expectation. Price equals the expectation of M times X. The discount factor M is nothing but state price per unit of probability. The chapter's one move is this. Pricing is an inner product. M is the vector you project payoffs onto. From that geometry alone, with no utility and no preferences, 3 facts drop out. M exists, M is positive, and the price map is linear. Everything later is this picture generalized. Here it is exact, and M is unique because the market is complete. This section explains how a single equation prices every asset in a market. One relation, the price equals the expected value of M times X, prices every asset by pairing its own payoff X against a single object, M, that is shared across all assets. That factoring is the entire move. Risk correction lives wholly in how each payoff covaries with the one common M rather than being computed asset by asset. Write the expected value of M times X as the expected value of M times the expected value of X plus the covariance of M and X. The covariance term is the risk premium. Under certainty, me collapses to 1 over the risk-free return, the ordinary discount factor. Uncertainty makes M stochastic, and its randomness is where all risk pricing hides. Every asset pricing model is then just an alternative bridge from M to data. You elaborate the connection once, not once per asset. One universal object discounts the whole market. This section explains a backwards move in asset pricing. Rather than build the discount factor M out of utility and beliefs, ask the inverse question. Given only observed prices and payoffs, when does some M exist that reprices everything by the rule that price equals the expected value of M times payoff? The thesis of the chapter is a duality. A property of the entire payoff space collapses to the existence of a single object that generates it. The law of one price, meaning that price is linear in payoffs, holds if and only if a discount factor exists. The stronger condition? No, arbitrage, meaning that better payoffs cost more, holds if and only if a positive discount factor exists. So no free repackaging is equivalent to me exists, and no free lunch is equivalent to me greater than 0. You buy the whole machinery of price equals the expected value of M times payoff without assuming anything about investors. This section shows that one object appears in 3 coordinate systems: the mean variance frontier, the boundary of the means and variances that portfolios can reach, and the expected return. Beta line, where average return rises linearly in a regression slope, are a single fact. Both are the discount factor of the previous chapter, wearing other clothes. The step that does the work is this. Pricing content is a restriction. The demand that a single intercept gamma serve every asset at once. Running a regression is free. Forcing one shared intercept is the entire theory. The law of one price alone forces the frontier to exist, the same premise that forced the discount factor M to exist. Everything downstream, CAP-M and APT included, is only choosing which frontier return to call the factor. This section explains what Chapter 5 is for. Its whole job is to hand you the translation dictionary. There are 3 dialects and 1 content. The discount factor sentence, P equals the expected value of M times X, says exactly what a mean variance frontier says geometrically and exactly what an expected return beta line says statistically. Nothing new is priced. The same content is only respoken in a different tongue. The generative move is this. A beta is a regression coefficient, the exposure of an asset to a risk factor, and lambda is the price of that factor. Average returns then fall on a straight line, exposure times price. The constraint the rest depends on is that returns must depend on how an asset behaves. Its betas, never on who it is, its size, its book, to market, its ticker. Otherwise, repackaging small firms into one holding company would mint free premia, and no equilibrium survives that. This section explains why the discount factor, the reference variable of a beta model, and a return on the mean variance frontier are 3 notations for one object. The discount factor, μ, in the pricing equation, where price equals the expected value of M times X, the reference variable of a beta model, and a frontier return, each carry identical information. Hand me anyone, and I generate the other 2. The chapter's entire content is that closed loop of mutual implication. The discount factor implies the frontier implies the discount factor, betas imply the discount factor, and the discount factor implies betas. So the apparent zoo of pricing models collapses to dialects of 1 grammar. CAP-M lives in frontier language, the consumption-based model in discount factor language, factor models in beta language. They are 3 charts on a single manifold, and the atlas closes. Every later new model is a change of coordinates, never a new object. This part shows that 3 languages describe one object, a stochastic discount factor, where price equals the expected value of M times X, a mean variance, efficient return serving as a beta reference, and the frontier itself carry identical information wearing 3 faces. Theta we, a peta reference wearing 3 faces. From me, you project to X star, normalize to R star on the frontier, and read betas of it. Conversely, any frontier return makes a plus B times R MV a discount factor, and a return beta model makes M equals B prime F price everything. The chapter's entire labor is clothing this triangle in every direction. All 3 representations are equivalent. The surprise the equivalence hides is this: choosing between discount factor, beta model, and frontier is choosing a coordinate system, not a theory. This section explains why proving that a discount factor exists tells you almost nothing. Prove that a discount factor always exists, and you have proved almost nothing. The equation P equals the expectation of M times X imposes so little structure that it cannot be wrong. Every byte, economic, statistical, predictive, lives in the restriction M equals F of the data. never in the equation that carries it. The sting is the sample moment corollary. Place little enough structure on M, and the model fits any sample exactly by construction, so in-sample success is free. What remains as content is only the discipline restraining which factors you admit. The pattern generalizes past this chapter. A representation theorem, general enough to always hold, is empty. All content relocates into the constraints you add back. That emptiness is what the chapter exists to expose. The algebra was never the point. This section explains why proving that a representation always exists drains it of all empirical content. That is the chapter's whole move. Some discount factor, M satisfying price equals the expectation of M times payoff, exists whenever the law of one price holds. And some mean variance-efficient portfolio always prices a sample by construction. So writing price equals the expectation of M times payoff, or writing a beta model commits you to nothing. You can fish up an N times payoff, or writing a beta model commits you to nothing. The content migrates entirely into the constraint, which factors enter M, when M is written as a function of the data and Y. Discipline is the only thing being tested. The generative pattern is this. An existence theorem is a falsifiability sink. Whatever it guarantees, you must look elsewhere, to the imposed restrictions for anything the data could reject. This section explains why conditioning information adds nothing to the pricing theory. Every pricing statement is conditional. The price at time t equals the conditional expectation given today's information of M times X. Yet you never need to model the conditioning at all. Multiply price and payoff by any variable Z observed today. Unconditional expectations preserve the identity, the unconditional expectation of P times Z equals the unconditional expectation of M times X times Z. The scaled pair Z times X is simply another payoff carrying another payoff, carrying another payoff, carrying another price. So the statement that P equals the unconditional expectation of M times X holds verbatim on this enlarged asset space. The conditional theory thus carries no content beyond the unconditional theory applied to manage portfolios, the buy more. When Z is high strategies, this dissolves the hard problem. Rather than estimate how the moments of N returns bend to M signals with parameters soon outrunning the data, you add the scaled returns and proceed as if conditioning never existed, while still letting agents a la Hayek see more than you do. This section explains how conditioning information collapses into ordinary unconditional moments. Prices are conditional objects. The price at time t equals the time t, conditional expectation of the discount factor at time t plus 1 times the payoff at time t plus 1. That expectation is taken against the investor's time t information, which you neither observe nor can Meester's time. The chapter's move dissolves that problem rather than solving it. Multiply both sides by any instrument, zt, that you do observe, then take unconditional expectations, and the conditional model reappears unconditionally. The unconditional expectation of the price times zt equals the unconditional expectation of the discount, times the payoff times zt equals the unconditional expectation of the discount. Conditioning information becomes more assets. You add assets to the model, and the count of statistics you have to estimate stays the same. The law of iterated expectations is the entire engine. Let zt range over everything measurable at time t, and you recover everything measurable at time t, and you recover every conditional implication. So the whole apparatus built for price equals the expectation of the discount factor times the payoff transfers intact. This part explains the single move that every factor pricing model shares. Every factor model is one substitution. The stochastic discount factor, written M, is marginal utility, and marginal utility is unobservable. So M gets rewritten as a linear function of observable proxies. M equals A plus B prime times F, where F is a vector of factors. The reason for the substitution is that consumption data is too noisy to measure marginal utility directly. Instead, you name variables that track when investors are happy or unhappy, and you let M ride linearly on them. That single move generates the whole zoo. The capital asset pricing model, CAPM, picks the market return as the proxy. The intertemporal CAPM, ICAPM, adds macroeconomic state variables. Arbitrage pricing theory, APT, extracts factors statistically from the return covariance matrix. They are one equation, disagreeing only over which F stands in for happiness. Not rival theories, but the same substitution wearing different proxies. This section explains why every asset pricing factor is a disguise for one thing. Every factor is a stand-in for a single unobservable quantity, marginal utility, growth the true discount factor. Because that quantity, call it M, cannot be measured, you replace it with a linear function, a plus B prime F, built from things you can actually see. The entire zoo of models, the CAPM, the ICAPM, is just that one substitution wearing different disguises. Here is the generative move. Any general equilibrium story hands you an equation, consumption at time t equals some function, g of the factors at time t, linking consumption to observables. Substitute that into the first order condition and consumption disappears, leaving factors behind. So the chapter's thesis is a subsumption. All factor models are the consumption-based model plus assumptions. Choosing factors is nothing but naming the bad states investors most fear, then finding variables that flag them. This part explains what generalized method of moments is at its root in the setting of explicit discount factor models. Every asset pricing model collapses to one sentence. Price equals expected discounted payoff. In symbols, the expected value of M times X equals the expected value of price, which you rewrite as a mean that should vanish. The expected value of M times X minus price equals 0. Generalized method of moments is nothing more than this. Pick the model's parameters to drive the sample mean of that error towards 0. Then test whether what remains is statistically 0. Cochrane's own compression is the whole chapter. The variance of a sample mean is probably the first statistical formula you ever saw, and in generalized method of moments, the last as well. Everything downstream, the weighting matrices, the standard errors, the over-identification test, is just the sampling distribution of a mean generalized. The pricing error is the moment condition. Nothing else is ever estimated. This section explains why one shape of equation stands behind every asset pricing model, and how a single estimation machine turns that shape into something you can fit and test. Every asset pricing model makes one shape of claim, price equals expected discounted payoff, so the error M sub t plus 1 times X sub t plus 1 minus P sub t has mean 0. That single form, the expectation of U of B equals 0, is the entire handle. GMM does the only natural thing. It chooses parameters B that drive the sample mean of that error as near 0 as it can go, then reads the model's verdict of how much error refuses to vanish. The distribution theory here is nothing exotic. It is the sampling distribution of a mean, generalized. The primitive to keep is this. Any economic restriction you can write as an expectation is 0 becomes estimable and testable by one machine. The errors define the moments, minimization fits the parameters, and the leftover pricing error is itself the chi-squared test. Chapter 10 is Hansen and Singleton's recipe. This section explains why every estimation procedure in the chapter is one setting of a single knob. Everything you could estimate is one choice of which moment conditions to zero. That is the whole chapter. Fix a model as the statement that the expected value of f of xt and b is zero. Then the A matrix, the linear combination of sample moments you set to zero, is the single free knob. Every named procedure is just one setting of A. The settings include correlation standard errors, ordinary least squares with autocorrelation, corrected errors, press beside weight asset tests, the real business cycle move of calibrate, then evaluate, and individual pricing error. 2 master formulas, the variance of B hat and the variance of the moments, G, T, then emit the sampling theory for all of them. The optimal A equal to D prime times S inverse is only one point in that space. The chapter's move is refusing to privilege it. This section explains how estimation collapses to a single template. Estimation stops being a zoo of methods once you see the one template underneath. A model is any set of moments that should average to zero, the expected value of f of x and b equals 0. An estimator is a choice of which linear combinations of the sample moments you force to zero, the selector A. BICSA and the sampling distribution of your estimate falls out mechanically from 2 formulas. That is the whole apparatus. Every new technique in the chapter is the same template with a different selector. A. Standard errors of a correlation, OLS with autocorrelation. Corrected errors, real, business, cycle calibration. Waiting away spuriously quiet portfolios, each one is just a different A. The chapter's work in the book is to convert GMM from a recipe into a universal solvent for estimation questions. This section explains what a linear factor model actually claims and why one restriction carries the whole chapter. A linear factor model, whatever economics it dresses itself in, makes exactly one falsifiable claim. Regress each asset's return on the factors, and every intercept, the alpha, which is the pricing error, must be 0. The entire chapter is apparatus for testing that single restriction. Its geometric dual is the compression worth keeping. All alphas equal 0 if and only if the factor portfolio sits on the mean variance frontier. So the question is the model true? And the question is, this factor inside the ex-post frontier only by sampling luck are one question in 2 coordinates. Time series versus cross-sectional regression are merely 2 charts over that one null. The Gibbons, Ross, Shanken statistic just measures how far inside the frontier the factor fell. This part explains why every way to test a linear factor model collapses to one question, and the chapter's gift is seeing that the question is trivial. Do the regression intercepts vanish? Regress each asset's excess return on the factor. The model, which says expected excess return equals beta transpose times lambda, puts all of the expected return into the slopes, beta. So the leftover constants alpha, the pricing errors, must be 0. The test statistic is then just a quadratic form, alpha hat transpose times sigma, inverse times alpha hat, the sample means over their covariance, distributed chi-squared, or the finite sample f of the GRS test. The move that makes the whole argument go through is that this same alpha equals 0, reads geometrically as one question, is the factor on the mean variance frontier. One primitive, intercepts are mispricing, generates every test in the next 3 chapters. This section explains why the discount factor form of GMM for linear factor models collapses into something you already know. Choose the pricing errors themselves as your GMM moments, and the entire estimation collapses into a cross-sectional regression. Average prices regressed on the second moment of payoffs with factors. That is the whole chapter. The discount factor form, M equals B prime F, fed through GMM, reproduces the regression estimates of Chapter 12. Exactly. The very same numbers rather than a mere resemblance. The weighting choice sets which regression you get. A first stage weighting, where the weighting matrix equals the identity, gives OLS across assets. A second stage weighting, where the matrix equals S inverse, gives GLS. The model, the expectation of B equals the expectation of XF prime times B already is a linear relation, so fitting it already is a linear regression. GMM adds only one thing, the correct standard errors for correlated pricing errors. The surprise is the deflation. A formidable sounding apparatus turns out to be ordinary, least squares wearing different notation. This section explains why Chapter 13, the body, adds no new estimation machinery. Write the model as P equals the expectation of M times X with M equal to B, transpose times the factors F. Take the pricing errors themselves as your GMM moments, and the estimator stops being new machinery. It is a cross-sectional regression. First stage OLS, second stage GLS, standard errors. The textbook residual formulas. That is the whole chapter. The surprising part is that GMM on the discount factor form recovers the very estimates the beta approach of Chapter 12 produced. The method is a change of coordinates, not of content. What pins the answer is the choice of moments, not the algebra. Once inside this frame, every downstream test becomes one routine. Does one factor drive out another? Is a factor priced, which the coefficient B captures, versus merely correlated with the discount factor M, which lambda captures? Does a return expand the frontier? One question after another, all the same procedure. This section explains the principle of maximum likelihood. Pick the parameters under which the data you actually saw was most probable. That is the whole principle, and everything else is its shadow. What makes it structural rather than a recipe is this. Differentiate the log likelihood, and the first-order condition is nothing but a sample moment set to 0. That moment is the score, the partial derivative of the log of f with respect to theta, and it is the gradient of your surprise. So maximum likelihood is GMM, the engine of Chapter 11, with one privileged choice of moments. Given a statistical model, it names which moments carry the most information. That is its office in the book. Rather than standing as a rival estimator, it is the thing that justifies the regression tests, telling you why certain moments and no others are the efficient ones to hit. This section explains where maximum likelihood sits inside GMM. Maximum likelihood is a single idea. Pick the parameters under which the observed data is most probable. Chapter 14's single move is to place that idea inside GMM as a special case, rather than treating it as a rival method. Here is why. Maximizing the likelihood means setting its derivative to 0. That derivative is called the score, and requiring the score to average to 0 across the sample is exactly a GMM moment condition. So maximum likelihood adds nothing to GMM's machinery. What it does instead is answer the one question GMM leaves open. Which moments? Given a statistical model of the data, the scores are the statistically most informative moments. Maximum likelihood is the moment selection principle. This is what justifies the regression tests that came before. This section explains why 3 procedures for testing linear factor models are really one estimator seen through 3 coordinate systems. 3 procedures that look methodologically distinct: time series regression, cross-sectional regression on betas, and GMM on the discount factor, are one estimator wearing 3 coordinate systems. Each draws the same line of average return against risk. They differ only in the weighting matrix that decides which pricing errors to tolerate. OLS, the first stage, weights all assets equally. GLS, the second stage, weights by residual covariance, and it collapses onto the time series line exactly when the factor is itself a return that the test assets span. Run all 3 on the CAPM over the CRSP size portfolios, and the estimates, the standard errors, and the chi-squared statistics coincide nearly to the digit. The chapter's job in the arc of the book is to dissolve the suspicion that the new GMM and SDF formulation is a different animal. It is not. It is the old regression under a reweighting. This section explains why 3 tests that look like rivals are secretly one test. There are 3 names for one test: time series regression, cross-sectional regression on the betas, and the ZMM discount factor estimator. All look like rival machineries. Cochrane's whole point is that on the classic exercise, running the CAPM on size-sorted portfolios, they hand back almost exactly the same estimates, the same standard errors, and the same chi-squared pricing error statistics. The apparent difference is only which matrix weights the pricing errors. OLS weights them equally. GLS weights them by the residual covariance. Second stage, GMM weights them by the spectral density. Everything else is the same. The new discount factor formulation that people distrust is the same object seen from another coordination that people distrust is the same object seen from another coordinate. Here is the predictive residue. Whenever a method claims novelty, ask what it weights. If the weighting coincides, the answers must coincide too. This section explains why the choice between maximum likelihood and the generalized method of moments is not really a contest at all. The maximum likelihood versus GMM war is a category error. Maximum likelihood is a special case of the generalized method of moments, one particular statistically optimal choice of moments. Once you see it that way, the only real axis is which moments to match. You can match the ones an auxiliary statistical model certifies as efficient, or the ones that carry economic meaning and survive being read directly. Efficiency is optimality relative to a true model. But every economic and statistical model is at best a quantitative parable, so squeezing out the last drop of efficiency optimizes against a fiction. Misspecification is the hidden variable here. It converts the choice of estimator into an insurance decision. You trade efficiency, which you can only claim under a true null, for robustness and interpretability, which you can actually see. Ordinary least squares beating generalized least squares is the same move. This section explains why the whole business of estimation reduces to a single choice. Every estimation method is a choice of which moments of the data to trust. Maximum likelihood is a special case of GMM. The moments its score functions prescribe are the statistically efficient ones, optimal only when the model is exactly true. But models are quantitative parables, always misspecified, squeezing out every scrap of efficiency, then overfits a fiction. So the working choice inverts the textbook one. You trade efficiency for the robustness and economic interpretability of intuitive moments, OLS, over GLS, regressions a reader can see through. This chapter's place in the arc is to dissolve the ML versus GMN debate into one knob. That knob is moment selection, and it is turned by how much you distrust your own model. This section explains why option pricing is where the book's central problem gets solved almost for free. The whole book runs on one equation. Price equals the expected value of M times X. Every chapter is a fight to pin down M. Options are where that fight is won, almost for free. Take the stock and bond prices as given and demand only that a positive M exist that reprices them. No cap M, no utility, no economics of M at all. In one period, that alone merely brackets the option through put-call parity and arbitrage bounds. Open up dynamic trading, force a single M to reprice both the stock and the bond at every instant, and the discount factor collapses to a point. Black. Scholes falls out as the expected value of M times X. This is relative pricing at its purest, value read off other prices rather than off a model. This part explains how a single pricing equation tightens into one exact option value as you add assumptions. The whole chapter still rests on C equals the expectation of M times X, and it turns one dial, how tightly the already observed stock and bond prices pin the discount factor, and therefore the option written on them. Demand only that some prices them, the law of one price, and you get put call, parity, and identity. Add that M is greater than 0, no arbitrage, and you get bounds, a range. Add that M must price stock and bond at every instant to expiration, dynamic trading, and the range collapses to a single point. Black Scholes. The surprise that makes this matter is what that point does not need. No cat M, no preferences, no model of M. Every valid discount factor returns the same option value, so the exact price is the law of one price alone. This section explains why Black and Scholes can price an option exactly, and what happens to that price when the conditions behind it fail. Black and Scholes price an option exactly because the option is redundant. A self-financing portfolio of stock and bond replicates its payoff, so the law of one price pins one number. That is the degenerate case. Junks, stochastic volatility, transaction costs, and non-traded underlyings each sever perfect replication. An irreducible basis risk survives the best hedge, and the price becomes an interval rather than a single point. Every positive discount factor that prices the traded assets gives a valid option price, and there are many. Pure, no, arbitrage bounds, positivity alone are too wide to use. So Cochrane and Saarekeho cack the discount. Factor volatility, the Sharpe ratio, excluding both arbitrage and implausibly good deals, and reclosing the interval to something usable. This is the Hansen and Jagannathan bound turned into a pricing tool. This section explains the good deal bound, the dial that sits between two broken ways of pricing, an option. Perfect replication is the crutch that lets Black and Scholes name a single price. Remove it, and pricing collapses to two useless extremes. At one extreme sit the arbitrage bounds, which ask only that the discount factor stay positive. That constraint is too wide to trade on. At the other extreme sit the absolute models, where M is fully pinned by a consumption story or a factor story. That constraint is too strong to trust. The good deal bound is the dial between them. You price the option as the maximum and the minimum of the expected value of M times the contingent payoff X, taken over every positive discount factor that reprices the traded basis assets and whose volatility stays capped. The cap says the volatility of M stays at or below H divided by the risk-free return RF divided by the risk-free return RFF. That cap is a sharp ratio ceiling. You forbid implausibly good deals, a stronger ban than ruling out arbitrage alone. One knob slides continuously from relative pricing to absolute pricing. Constrain the admissible set of discount factors harder, and the price interval tightens. Every pricing doctrine is just a choice of that constraint. This section explains why pricing the term's structure of interest rates collapses to a single expectation. A zero-coupon bond is the cleanest asset in the book. Its payoff is a certain dollar, so pricing strips down to one statement. The price at time t of an n-period bond equals the conditional expectation, taken at time t of an n-period bond equals the conditional expectation, taken at time t of a chained product of one-period discount factors, running from the factor for t plus n, that is nothing but the conditional expectation of a chained product of one-period discount factors. That every richer object, the yield, the holding period, return, the forward rate, is an invertible re-quoting of that same price and adds no assumption. The modeling content lives entirely in the process you posit for the single period discount factor, μm. Cochrane's framing is that the term structure is particularly simple because the payoff carries no risk. So all the machinery is technical, how to chain the m's, forward by integration, or backward by a partial differential equation. This section explains how bond pricing falls out of the book's single equation. Price equals expected discounted payoff. The one equation of the whole book collapses here onto its most trivial payoff, a single certain dollar at a future date. A zero-coupon bond carries no payoff, uncertainty, so pricing it demands nothing but the chaining of one-period discount factors forward through time. Written out, the price at time t of a bond return j periods ahead equals the expectation at time t of the product of the successive one-period discount factors m from t to t plus 1 times m from t plus 1 to t plus 2, and so on, up through m from t plus j. That identity is the whole chapter. Yields, forward rates, the expectations hypothesis are each only a change of coordinates on that one expectation, a convenient way to requote the same price. The entire apparatus of term structure modeling is the technical question of how to perform the chaining. The economics was finished at the first line. This section explains why the whole chapter turns on a single fact. Expected returns are not constant. Cochrane sets this as the empirical pivot. The first revolution, meaning the capital asset pricing model, the random walk, and efficient markets, said that returns are unpredictable and that market beta prices everything. A second wave of careful empirical work overturned every plank of that view. The generative move is that this one fact fractures along two orthogonal axes of the same object. Vary the conditioning time and you get predictability. The dividend price ratio forecasts returns, and it does so more strongly at longer horizons. Vary the asset and you get the cross-section, average returns that market beta cannot explain. Both are the same pricing relation, the expectation of m times x, read twice. Once you hold the asset fixed, once you hold the date fixed. The chapter is the target that the rest of the book's machinery must now hit. This section explains how two revolutions in finance fit together and why the second one did not overturn the first. The old creed read market efficiency as a single claim. Returns are unpredictable. The new evidence says they are predictable. Dividend over price forecasts stock returns, steep yield curves forecast bond returns, and forecastability climbs as the horizon lengthens. The reconciliation is the whole insight. Efficiency never forbade predictability. Efficiency never forbade predictability. It's Trumber. Here is the mechanism that makes the two agree. A high price of risk in a recession pushes prices down now, so low prices mechanically forecast the high returns needed to hold stocks. Then, predictable expected returns are time. Varying risk premia, not free lunches. The discount factor simply became conditional. Same logic as before, now moving through time and across many factors. This section explains why the equity premium looks like a puzzle, and the whole thing descends from a single inequality. The Hansen and Jagannathan bound says that any asset's Sharpe ratio cannot exceed the standard deviation of the stochastic discount factor divided by its mean, which is to say the volatility of that discount factor. That one object, the stochastic discount factor, that one object, the stochastic discount factor, that one object that prices every asset. Under power. Utility, the discount factor is marginal. Utility growth, so its volatility collapses to something simple, risk aversion times consumption, volatility, gamma times the standard deviation of log consumption. Now, measure the world. Post-war stocks carry a Sharpe ratio near 0.5, yet aggregate consumption barely twitches, its volatility roughly 1%. Reconciling those two numbers demands a risk aversion near 50 and near 250 once you admit that consumption and returns are not perfectly correlated. The surprise is that the single quantity pricing these returns is far too smooth to justify them, even though the returns themselves are only ordinarily high. So one of three things must give. Either people are implausibly risk-averse, or the last 50 years were luck, or the marginal utility engine is wrong. This section explains the structural move behind the equity premium puzzle. The step that makes the whole argument go through. That move is inversion. Instead of proposing a utility model and testing it, you read the required properties of the discount factor straight off the data. The market Sharpe ratio sits near 0.5, and by the Hansen, Jagannathan bound that forces the standard deviation of the discount factor divided by its mean to be greater than or equal to 0.5. But power utility ties that standard deviation to gamma times the standard deviation of consumption growth, and consumption growth wobbles only about 1% a year, so risk aversion must be around 50 to price stocks. That same gamma then predicts wildly volatile high interest rates we never observe. The puzzle is a lower bound. The canonical model misses by 50-fold. The chapter's function in the arc is this. It converts a failed model into a specification. Whatever prices assets must be this volatile, yet this conditionally quiet. This section explains continuous time as the limit of discrete time. ARMA. Continuous time is discrete time. ARMA, with the step shrunk to 0. Nothing more exotic. The whole appendix hangs on one algebraic rule. dz squared equals dt. Ordinary calculus throws squared increments away a second order. Here, the shock square survives exactly because a random walk's variance scales linearly with time while its path stays non-differentiable. Grant that single fact in everything regenerates. Brownian motion is the random walk limit. Every diffusion, dx equals mu dt plus sigma dz, is an ARMA analog. And Ito's lemma is just a second order. Taylor expansion with dz squared equals dt retained. The lone surprise, Ito's extra drift term, is a Jensen effect. Curvature times variance. One rule, and the entire calculus falls out. This section explains why Ito's lemma is simpler than its measure. Theoretic reputation suggests. A random walk's typical step scales as the square root of dt, so its square scales as dt, Because the variance of that square shrinks one order faster still, the square stops fluctuating. We get dz squared equals dt, exactly, a deterministic term that survives into first order while dt squared and dt times dz vanish. That single rule is the whole appendix. The imposing measure theory of continuous time collapses into a second-order Taylor expansion with everything passed, order dt discarded, which is all E2's lemma is. Cochrane's promise runs like this. With a few basic intuitive rules like dz squared equals dt, you can use continuous time processes quite quickly. The generative move is to keep order, dt terms only. A path too jagged to differentiate becomes ordinary calculus.